Alright, let's talk about the Banach fixed point theorem. It is also known as the contraction mapping principle theorem. It has quite a few names. So here's the table of contents. Let's talk about some motivation for why we are talking about this theorem. So the Banach fixed point theorem is, well, you can see it commonly. Well, not commonly. You can see it in higher math, advanced math proofs, which is, for instance, the Picard-Lindelof theorem, which is the existence and uniqueness theorem for ODEs, and the inverse function theorem, which we covered in MA2 a few weeks ago. The general Banach fixed point theorem, the statement is, well, it is made sense with definitions from the notion of metric spaces, which is, well, what we didn't really cover deeply. We just brushed it over in MA2. But anyways, here for simplicity, we just focus specifically on Rn, which is a complete metric space. And note that complete here means that complete here for metric spaces, completeness is a property for metric spaces, such that it states that for every Cauchy sequence in the metric space, it will converge. And for Rn, it is, and therefore for Rn, which is a complete space, therefore we know that every Cauchy sequence in Rn will just converge to some point. Will basically converge, yes. Now, here's Stefan Banach. He's where the name Banach fixed point theorem comes from. And he is also well known for Banach spaces, which is a complete normed vector space. We won't dive into that, we won't talk about that. And he's also known as the founder for functional analysis. But yeah, and here's two pictures of him, and the right one where is him at 44 years of age, and this is the one that you will normally find on the internet. Alright, let's do this. The main theorem. The Banach fixed point theorem on Rn states that if we let D to be a closed subset of Rn, closed here captures the completeness property of metric spaces, and let F let F be a function D to D, and it's a contraction, then F must admit a unique fixed point U in D. So before we dive into the theorem, before we dive into the proof of the theorem, let's just do a quick detour, and let me tell you what the theorem is talking about. Quick disclaimer, I didn't think of this on my own. This idea was obtained from the internet, YouTube videos, like exchange. So let's consider, I'm not going to read the experiment for you, but I will just show you what we are doing. Okay, it works. So I have this picture here, and then I make a copy of it, smaller, and I made it transparent, more transparent, so that we can see what's going on later. So now, notice that if we look at this, two pictures, the big one and the smaller copy of it, I resize it and I place it at some point within the bigger picture, and what we can see is there is one point here that overlaps between the two copies, right? There's one point there that overlaps. and there will only be one point. Let's do this for a few more examples. Let's say I move the picture, maybe let's say here. Okay, so we'll move it here. Where's the point that doesn't move? Well, it will be this point, right? It's gonna be somewhere around here. But yeah, that's the idea of what's going on. It's not a proof, right? And clearly, if I move the picture up all the way here, the fixed point will be just the top left corner, the bottom left, bottom right, bottom and top right. So yeah, and showing that there exists a fixed point here is easy, but showing that there only exists one, that's a bit hard. But anyways, let's go back to our right, let's do the proof. So the proof will be split into two parts. One part will be showing that the fixed point exists, and the other part will be showing that the fixed point is unique. So here, let's do this. Here, let's come back to the statement. So you have D to be a closed subset of Rn. F is a function defined on D to D to be a contraction, and F must we want to show that F admits a unique fixed point theorem, a unique fixed point U in the domain D. Okay, since F is a contraction, by definition there exists a constant, a Lipschitz constant within 0 to 1 such that this holds. And then, since it holds for every 2 points UV, any arbitrary points UV in D, let's consider x0 in D, some point x0 in D, and consider the sequence xk. And we define the sequence such that xk plus 1 is equals to xk for k greater than 0. Now, since these x not xk are all in D, therefore the contraction applies to all of these xk's. So for k greater than 0, the xk plus 1 minus xk will be equal to this. This is because, so xk plus 1 minus xk is equals to fxk minus fxk minus 1 because of this, because of the definition of how we define the sequences. And then, since this is a contraction, f is a contraction, therefore this must be less than this. Okay, so we have this inequality here. You know that I can apply the same idea on this term. So therefore C of xk minus 1 is going to be equal to Cf x minus 1, and then by the contraction again, it's going to be less than some c squared term, and I can do it, and I keep doing it. After k iterations, we just get this. Now, just remember this equation 1, real quick, because we are going to be using it now. Okay, here I'm going to show that the sequence xk, which we defined earlier, is a Cauchy sequence. So let epsilon be greater than 0, and then note for L greater than k greater than or equal to 0. We want to note that we want to prove it for L greater than k greater than or equal to some k, but let's do 0 for now. The xl minus xk is going to be less than this thing because of the triangle inequality. the triangle inequality works for Rn, and actually it works for metric spaces if you would like to see the general proof. But yeah, basically that. Because of the triangle inequality, we have the first inequality here. Then the second inequality here, it follows from equation 1, which is this. You apply equation 1, and then since, well, we see that all of these are like powers of greater than, yeah, some k, right? So let's factor c to the k out, and then we are left with this, and we see that this is basically a geometric sum. So we can write it as a geometric sum instead. And then here's something that we can think about, that if we have a geometric sum and it is finite, it is a finite geometric sum, and note that the terms here, well, c is from 0 to 1, and then the distance is always greater than 0, it's positive. Therefore, if I'm summing finite positive terms, it is going to be less than summing infinite positive terms. So this is how this step follows. And then finally, we know that this is the geometric series. So we have the geometric series formula. Great. And then next. Okay. Therefore, we have shown for L greater than K greater than or equal to 0, this thing holds. Now, since C is in 0 to 1, then there exists a positive integer k, big K, such that for all k, small k greater than or equal to big K, this holds. Well, basically, C is small, right? Because C is small, and you throw some integer power k, which is like which keeps being bigger and bigger. This term will just go to 0, and therefore for any small epsilon you find, I can always find a very big k such that this whole term goes to 0 faster than epsilon. Okay, and thus we have shown for L greater than K greater equal to K that this term is less than this, less than epsilon, therefore this is less than epsilon, which is the definition of the sequence being Cauchy. Great. So now we have shown that the sequence is Cauchy, and then since the set D, since the domain D is closed, it must converge. Since the sequence is Cauchy, it must converge. Since the sequence is Cauchy and the domain is a subset of Rn, which is complete, it must converge to some point u in Rn. It must converge to some point u. But then, since D is closed, I mean, it must converge to some point u in Rn, but since D is closed, then u must be in D, yes. Okay, then since f is contraction, which is Lipschitz, and we know that Lipschitz functions are Lipschitz continuous, uniform continuous, and therefore continuous, the sequence fx converges to fu, which means fu equals this, which is basically just this line here. And then since we know that the function f is uniform, it's continuous. Wait, no. Wait, since f is continuous, this line, this equality holds, then we know that fxk is defined to be xk plus 1 by the sequence, by the definition of how we define the sequence. And then finally, this equality here holds because xk plus 1 is basically just a subsequence of xk, and xk converges to u, therefore the subsequence must also converge to u. And then we would have fu equals to u, which is a subset, which is a fixed point, which means u is a fixed point of f. Yep, because u is in D. Yeah, and this basically sums up the existence of the fixed point. Right, now here we will prove about the uniqueness of the fixed point. So suppose u and v are distinct fixed points of f, and then it holds that it exists. So let's just suppose there are two different fixed points, and then we will show that u equals v, and therefore it must be unique. Since f is a contraction, therefore there exists c equals c in 0 to 1, such that, okay, here's the first inequality. The distance of uv equals to fu minus fv, because u and v are fixed points, therefore it means u equals fu, v equals fv, which is therefore, yeah, this equality here. And this equality holds because it is a contraction. Easy. Then since c is in 0 to 1, then equation 2, which is this, basically this part, it must hold only when c equals 0, because c is like making the distance smaller, and then a number to be smaller than a smaller, basically that. So it only holds when c equals 0. Therefore this holds, and then if this is 0, by definition, well, no, and by a theorem, no. But basically, if the distance of 2 points is 0, then it is just the same point, right? And therefore we have shown that the fixed point of f is unique. Great. Okay, now let's talk about, so as we mentioned before, the Banach fixed point theorem is used in the proofs of the Picard-Little theorem, Yama's function theorem, and it is also used for image processing in a paper. But such examples are too complicated, and it's already been 25 minutes of a presentation. So let's leave that for another day, and here's an easy example instead, from a textbook. So here's the example. Let Sn be the n sphere, and f to be a mapping Sn to Sn, such that it satisfies this inequality, and we are to show that there is a unique fixed point w in Sn, such that, fw equals w. So basically this is saying that, show that it is a fixed point, right? So first thing to note that Sn is a subset of Rn, well, basically, but actually Rn plus 1, and it is closed because we can see that it is closed. So we have a subset a subset of Rn that is closed, Rn plus 1 that is closed, and then we see that f is a mapping such that this, and we see that this is basically we definitely see that f is a Lipschitz function, and then the constant is 2/3, which is in 0, 1. Therefore f is a contraction, and we have shown earlier, if f is in contraction, then it must have a unique fixed point, and therefore we are done, because f is a contraction, and therefore it has a unique fixed point w. It must have a unique fixed point, such that that's it. And alright, thanks for your attention. It's been 28 minutes. Well,